Yeah, all right, everybody. Hope you had a good lunch. We're going to talk about some observations here. Like we discussed yesterday, observations do matter. So we're going to try to show the value of these observations as it relates to the modeling system. So Stephanie's up first, and we will go. We have 10 minutes, so I will give you a warning a couple minutes before.
Now it is.
Okay, now you guys can hear me. All right, so good afternoon. As you said, I'm going to talk about hurricane observations and kind of give a user perspective from NHC. I really want to focus today on what types of observations we're using at NHC, why they're important, and some of the challenges and subjectivity that can come along with analyzing observations and having to make an analysis on a tropical cyclone. I am hitting it and it is doing nothing.
It's still not working.
All right. So the important,
Just yell out next
I will do that. All right, so the importance of TC observations, we all know this, but I just wanted to kind of outline it here. A lot of the observations that we take from satellite aircraft and conventional observations are the foundation for what goes into what ultimately is the best track data set. The best track is used for a variety of things. We've looked at a lot of model verification this week that uses the best track as the truth value. It's used by the research community, and now that we're in this AI realm, a lot of AI models are trained using the best track, or trained against the best track. We also know observations are important for initializing the models. Next slide. This is the same chart that we showed at the last hurricane observations HFIP session last year. Lisa Bucci put this together, one of the hurricane specialists. This is kind of the current state of what's used for getting different measurements in a cyclone, whether it be the intensity, the structure, or the size of the storm. Nothing really surprising on this list here, but one of the caveats of all these is that they vary in coverage in both space and time. So as Chris mentioned earlier, we don't have aircraft data in a lot of storms. We end up relying on satellite, mostly geostationary satellite, but we can get some information from our polar orbiters. And of course, we have, occasionally we get lucky when a storm goes over, a buoy or close to land. Next slide. I have no idea if this is 100% accurate, but I tried to put together a timeline of how all these different observations have evolved over time. So we've had aircraft recon for a while. We've gotten more observations and more instrumentation on the aircraft over time. And in recent years, things like SUAS, which I'm sure we'll hear about later. Weather satellite-wise, our satellites have continued to improve. We have more satellite data. One of the things that NHC is evaluating now is SAR, which can give us estimates of surface wind speed, and I'll touch on that a lot later in the talk, because sometimes when you're incorporating new observations into operations, it can be difficult to understand how best to use those observations. So one of the things I want to mention here is that as more OBS are added to our suite here, some of them may start observing parts of storms that we've never been able to sample before. These unmanned drones can go places where manned aircraft can't. And how will we integrate and adapt those observations into this whole workflow of our analysis of the storm and everything else? Next slide. So these next few slides, I want to just pick a few cases from the 2023 season where there was a 40-knot difference in what the observations were showing for the intensity estimation for 3 different cases. That doesn't necessarily mean the uncertainty was 40 knots, but just to show that sometimes it can be difficult when you're in the hot seat and you have to analyze how strong a storm is. So next slide. The first case, I don't have any pretty pictures to go along with it, but Franklin, which was an Atlantic storm, this was near the beginning of when it was about to intensify rapidly. At 0Z on the 26th, we had an aircraft data in there, or aircraft flight in there showing SFMR peak winds at 70 knots. The flight level reduced, suggested 55 knot intensity. And the satellite estimates from the human and the automated range from 30 to 45 knots. So NHC put the initial intensity at this time at 50 knots, but you can see there's a large spread. And if we wouldn't have had the aircraft data, I'm not sure it would have been set at that place. And of course, they go back after the season and reevaluate all the data. But just an instance where, you know, there's a large spread and it may impact what the intensity is set at. The next two are going to be SAR examples. So this first one here from Hillary, as I mentioned, we're trying to learn how to integrate SAR into our operations. This was a case on the 18th of August, 12Z, where Dvorak was suggesting the storm was somewhere between 115 and 132 knots. And the SAR pass was showing 94 knots. So a 30-knot discrepancy in what we were carrying at 125 knots from what the satellite was showing. So the next case is the exact opposite. SAR showed a 73-knot storm in Jose. The SAR pass is actually around 21Z this day, so I put the 18 and 0Z there for you to see. But you can see that it's way different from what the Dvorak was showing. And Jose was a small storm. The SAR pass showed it being small as well. But sometimes when we see these new observations, it can be difficult to know what truth is. So yeah, next slide. So I took all the FDECs that we have from 2023 with the fixes from the various platforms that we can get observations from and calculated the deviation from what NHC carried in the best track intensity, that's on the y-axis, with the deviation being in knots. So anything below the 0 line means that the observation suggested the intensity was lower than what we carried. Anything above means higher. And these are violin plots showing the distributions, and the line in the middle is the median, and the top and bottom are the extremes. So mainly focusing on the distribution, these observations tend to center around where we carry the best track. The two on the left are the two aircraft, the SFMR and the flight level. They're a little lower than normal because some of the fixes are flight legs that don't necessarily capture the maximum wind speed. The satellite ones, Dvorak and ADT and SATCON, all seem to be pretty relatively well centered around where we carry our best track positions. ASCAT has a little bit of a low bias, which shows up here because of how big the resolution of the ASCAT data. And then a couple at the end here, SAR. I mentioned SAR. That's the only one that has a line that's above 0. So it tends to be higher than what we carry on our best track. And you can see the extremes can be higher than any other observation as well. So this is some of the challenges that come with using all these different data sets. Thanks, but I only have one more slide. So next slide. Just when we think about new observations, some of the things that affect how it can be integrated into operations are how easily accessible is the data? Do I trust my measurement or have information about its reliability? Has it been validated and calibrated? And have there been any changes to the instrument recently? And of course, the specialists, when they're looking at all of this data, they have some idea of all of these answers and are able to make a best estimate of what the storm intensity is. So yeah, I'll end there and help get us back on track.
Yes, thank you. We will have a discussion at the end, so with the panel. So we'll move on to our next talk, and I guess is Jason giving this one?
Yep, I'm
Jason's
giving it.
online. So I guess take it over, Jason.
All right, sounds good. If someone could click for me as we go. Just want to acknowledge Heather Hublock and Rob Rogers.
Stand by, technical difficulties.
No problem.
Jason, can you try to speak up a little bit? We're having a real hard time, and our mic is pretty much halfway up the gain right now.
No problem. I expect 5 extra with all this. All right, looks good. Can you hear me okay?
Yes.
Okay, sounds good. So I just want to acknowledge Heather Hublock and Rob Rogers, just giving an overview of the AFEX efforts this year, what we flew and the kind of observations that we collected. Next slide. So AFEX is a partnership between several NOAA agencies, and we had special collaborations in 23, including PHOD, ONR, GOMO, and University of Washington, among many others. And really what drives our efforts are three goals. The first one is collecting observations that we can use for model initialization and evaluation. Goal 2 gets us more into the measurement strategies and technologies, things like small UAS. And then goal 3 is, to me, that all-important understanding of physical processes, everything from genesis formation, tensity change structure, and the hazards that come with them. And just pointing at the bottom, that's our data page that a lot of the data I'll talk about today can be found on that page or will be soon. Next slide. It's just a quick overview of our 2-hour on-station time on the left for the P3, the right for the G4, just to give you a sense of, we have a lot of coverage in the Atlantic for targets of interest, so it's a real advantage for us with these deployment sites. Next slide. Here's what we flew in 23. We had a couple of missions into early August tropical waves, followed by Franklin, Idalia, Lee, Nigel, and wrapped it up with Tammy. So these are all the P3 flights, G4 flights that we flew for both operations and research this year. So you can see we were quite busy with our field program. Next slide. Just a quick overview of the storms and the parts of the life cycle that we flew. There are the waves on the left. You can see the G4 and P3 tracks on the bottom left. That was followed by Franklin. We captured that one pretty early, right up until the point where it was getting close to rapid intensification. Unfortunately, we had to switch over to Idalia since it was threatening the Gulf Coast of Florida, but lots of great observations in that sequence as well. Next slide. Hurricane Lee, that was a long sequence from Cat 4-5 all the way to dissipation up near Canada, actually. That was quite a long sequence. That was followed by Nigel. We flew that out of Bermuda for a few days, and then finally wrapped up with Tammy at the end of October. With those were actually pure research flights. Next slide. Just kind of a season summary. Really won't go through all these. I would just like to point out that of the 37 P3 and 17 G4 missions, so 54 missions, HRD supported all of those in some manner, whether it was crewing the flights or doing ground-based support. We also had a lot of successful AXBTs, 90 this year, and kudos to our radar team for transmitting 188 TDR analyses to EMC for model assimilation and over to the Hurricane Center so the forecasters could see it. Looking at our successes, certainly the collaborations with partners, pre-season planning right up to the heat of battle during the season. I was really happy with that. Also HRD supportive operations, whether it's things like TDR or QC of dropsons and getting them on the GTS. Also tested new technology, Altius and Black Swift, small UASs, Micro Swift wave buoys, and Skyfora streamsons, these mini dropsons that maybe have some swarming capabilities in the future. We did a lot of basic research, rapid intensification, TC vortex alignment. I'll talk a little bit about that. SFMR validation were just a few of them. For us, travel to support those operations can be a challenge, and limited staff to really keep up with that really busy tempo that we saw in August and September. Next. Not going through all these are our experiments and modules for the season. Everything from Genesis, early mature stage, end stage with something like a landfall, also ocean observing and satellite validation. So you can see in bold are the ones that we completed this year, which was really good to see. It was about 14 experiments and modules that we were able to fly during the season. Next slide. Just looking at aircraft instrumentation, and this is more for the history of it rather than to go through the details, but flight level measurements from all 3 aircraft. Tail Doppler radar, I'll talk about that in a little more detail. We have the MMR X-band radar for looking at hazard avoidance out there in the storm. SFMR on the P3s and cloud microphysics probes. I'll talk a little bit about those as well. We had those on N43 this year. Next. Also, we had IRAP, so this is an instrument looking at Doppler velocity and reflectivity below the aircraft. And they also had their Kaya instrument for looking at wave heights on NOAA 4.2. And really nicely complemented, we had on NOAA 4.3 the WSRA also collecting wave measurements. This year, W-band flew for the first time in a long time during hurricane season. It's operating at 95 gigahertz, and it's able to detect very small water droplets of fog or mist, so you can start deriving things like vertical motion and rain rate. And then the ARO, so that's a GPS radio occultation system that flies during atmospheric rivers. We added that to the hurricane package, so it flew on 43 and 49, and you're able to get vertical profiles of temperature and moisture below the aircraft. Next. Lots of observations. I won't go through them all, but you can see who deployed what types of observations, from dropsondes to BTs. We had successful UAS deployments in Tammy, Skyfora, Streamsons, and Nigel, and a first ever microswift wave buoy launch from the P3 during the lease. That was great to see. And then also A-size wave drifters that we're able to put out through the BT chute on the P3. And we had several sail drone coordinations with the P3 with dropsondes and BTs in close proximity to the sail drones. So that was also a success for us too. Next. Just looking at TDR, we're able to get 3D winds, precip and precip type. On the left, it's from Franklin on the 21st P3 flight. It's 2 kilometer reflectivity. The right is showing, highlighting streamlines at 2 kilometers, that's in black, and 5 kilometers in gray. And I put L&M for the low and mid-level circulation. So takeaway here is that the vertical alignment of the storm just hadn't come together yet. It was still trying to get its act together. Next. A few days later, you can see reflectivity on the left is really starting to fill in. But we've also got the low and mid-level circulations really nicely aligned over time, so that evolution was very clear. And if you click next, one of our experiments is the VAM module. So we're trying to capture this alignment. So on the left, on the 21st, I tried to connect the times, the low and mid-level circulation for the 3 different passes. A lot of separation, 50 kilometers or more, as the storm convection is collapsing, convection is popping up again. So it's quite a mess when you're looking at those circulations. Contrast that to the 26th. First pass, we had a little bit of separation with the low and mid-level circulation. Same thing with the second pass. And then by 1527 and 1452, we had perfect alignment. So that evolution is really interesting to watch over time, and VAM helps us get more of those. Next. Just WSRA, just really quickly, Hurricane Lee on the left, several of our P3 missions, and Hurricane Tammy on the right, giving us significant wave heights. All that data is going to ground servers, and it's being used by TAFB in real time, which is great to see. Next slide. Just looking at our microphysics probes, we have 5 probes sampling at 0.63 microns to 6.4 millimeters. So the goal here is really to sample distributions and variability of cloud and rain droplets, ice and snow particles, as we go in that animation from flight level, say 10,000 feet through the freezing layer up to 20 to 25,000 feet. So lots of interesting data being collected. We had about 6 spirals, hopes to compare some of that information with what we're seeing in the models as well to do some validation there. Next. Trying to get as much data as we can off into the models. So in this case, Hurricane Idalia on the 28th of August. These are all the obs that got into HWRF and HAFS in real time. If you click next, we got flight level data in red and orange. Click next. Dropsondes, winds, and thermo from all of the missions. And then final click, a lot of TDR data. That's the bulk of it due to the swaths around the flight track, as well as we're getting that 3D slice through the storm. So there's a lot of data that we're getting off into the models in real time. Next.
1 minute, Jason.
Sounds good. What's up for next year? We'd like to collaborate with ONR's Magpie out of Barbados and continue our collaborations with NRL and ONR, looking at rapid intensification. Interesting to try to do some more Genesis work out of Cabo Verde in the East Atlantic, as well as Costa Rica over by the East Pac. You know, a storm like Hillary that affected Southern California would have been a great target for that. And also continuing the emerging technology efforts that we talked about. And then finally, satellite validation with JPSS, and definitely tropics. Now that that constellation is fully up, we'd like to try to have some missions to do some validation. And with that, next slide, I'll just say thank you. And I put the data link up there. Once again, if you're interested in checking out the data as it's starting to be populated for 23.
Well, thank you, Jason. Let's give him a round of applause. Some other guy from HRD's up next, talking about new technology. How are you going to advance this? You guys
just give us a second. We're transferring over to the other file.
multitask. I'll yell at myself too. Joe, you got 3 minutes left. We are ahead of schedule a little bit, so that's nice. We'll have a little bit, hopefully a little bit more time to discuss at the end. So while we're setting this up, this is some of the emerging technology that you heard of. A lot of what I've been concentrating on, the low-hanging fruit, if you will, for the last several years has been UAS, uncrewed aircraft systems, small ones. But we're jumping into other things now. So Jason mentioned something about stream SOMs, which are essentially lightweight drop SOMs that have some technology advantages that I'll go into here. I don't know if I can advance or not. Oh, hold on a second. Okay. So yeah, we'll dive into that. I will start once we get into this with a little bit from 2022.
We might have to do the slide movement here.
Okay,
The remote.
that's fine. Issues. I'll just stay next. All right. We'll start with 2022. So next slide, please. This is Hurricane Ian, which we've heard several talks about this. So this was the first time we flew an Altius drone, which has a potential duration of about 4 hours. We didn't quite get that, but it survived some serious turbulent conditions, as you'll see. Next slide, please. So that's what the Altius looks like. It's about it has 2 modes. That's the fully extended mode, which is about just short of 9 feet wingspan. But it can go in stubby mode, which for Ian, it actually flew in stubby mode, which is a little bit more stable, hits the endurance a little bit, but it can stay up in stronger winds. Next slide, please. So this is a pretty cool composite from Weather Service that I got. It's the radar mosaic, and you can see the storm emerging from Cuba there. And we basically flew our mission right before landfall. And you can see the double owl wall, and then it rapidly intensifies after that, which surprised a lot of people. At least it surprised us. And right about now is when we deployed the drone, just offshore. So next slide, please. This is where we don't usually operate from. Number 7 is out of Texas. We normally operate out of Lakeland, as you might imagine, but this storm was threatening much of Florida, so we had to deploy, which is, not a simple task. Those people sort of think, okay, where are you flying, with the hurricane hunters? And there's a lot of family issues that come into it, a lot of logistical issues, trying to set up in a different remote place. So I just want to shout out to them for being able to do that and getting credit for keeping us safe and still being able to operate. Next slide. So that last pattern, I should have said, you could see, we were planning on doing a butterfly pattern and doing all these special patterns, but in the end, the storm decides what we're going to do. So you can see the first line that's coming in, and then you can see the swirls in the middle on the edge of the lightning strikes, which are in yellow. And that's us deploying, coming through the southwest eye wall and then deploying the drone. You notice there's no figure 4s or anything else. We got out of there because that first pass was extremely turbulent, extremely strong winds, and we wanted to make sure that the plane was okay and didn't exceed any tolerances. So you can see that loop that goes all the way up to the northwest there. That's the P3 checking itself out and making sure we're okay. Meanwhile, that distance is about 130 miles. The last drone we flew could fly about 20 nautical miles, and we still kept communications, as you'll see. Next slide, please. So there's that scalloping in the southwest eye wall. This is a great 15-meter resolution image, and we flew right through that. The eye is not exactly clean either, so there's a lot going on here on the mesoscale and the microscale as well. So next slide. This is the path I showed you what the P3 looked like. This is the UAS. So you can see Jin Zhang put this together. It's blue is low winds, and you can see the scale. Maybe you can't. It goes up to about 200 knots. You can see the strongest winds in that southwest portion, and you can see us, the track, we essentially came at 5,000 feet and kept dropping down. You can see the red where we're at about 2,600 meters or so, where we really, really got some winds. Next slide, please. So this is vertical velocity. The inset is from the drone, which shows about 15 plus or minus, plus 15 minus 10 meters per second, and similar what we saw extremes from the plane itself, from the P3 itself. Next slide. So this is just to give you an idea for those not as familiar with observations and what pitch and roll. This is pitch, so the little cartoon tells you what that means. The pitch this was a lot of pitch for the P3. We could see pitch is basically about 10 degrees deviation from -6 to about -5. Now the drone itself, you can't see that scale, but it's about plus or minus 20 degrees. So it's a small plane. It's flapping in the wind. Next slide, please. This is roll, self-explanatory. A lot of roll here too. You can see that, you know, it's in minutes on the bottom there. So you can see in less than 30 seconds, we go from a +6 degree roll to a -15 degrees. So that's a lot. And the drone was even more. Next slide. Just a couple of ways to show data. This is air temperature, relative humidity, and everything else, air pressure, wind speed, altitude. So we got a pretty good estimate for the basic quantities that we were wanted to observe. So the PTH work, we were near saturated most of the time, but not always. You can see a couple times we got into dry air when we were in the eye. The wind speed there, about 7,000. You can see that was when we came close to our maximum winds of almost 200 knots, like 215 miles an hour. Next slide, please. So we set some records. Actually, the Guinness people called us and said, they said, did you set any record? They asked us. Well, yeah, we actually did. We did 3 of those things. For whatever reason, they picked number 2, which is the endurance, which is the one we'll probably shatter the next time we fly. But those are some records that particularly the distance from the P3 is a big deal. The wind speed might be the strongest wind speed ever recorded by a drone, period. I can't, you know, I don't know what DARPA is doing, but they're probably not flying in hurricanes either. So recently we flew in TAMI, and we also had some missions into some streamsong missions into Nigel. Next slide, please. So this is the sail drone interaction. Got this from Lev. I don't know who actually created it, but stole this from you. You actually have probably seen this already. So you can see the P3, they're doing its spirals that Jason just talked about, and that magenta hook there, it's really what the P3 did, and you can see the sail drone. So we got close within about 18 nautical miles, tons of coordination to pull this off, not easy. And thanks to everyone involved, both from the sail drone side and from the NOAA side, from the UAS side. Next slide, please. So this is what that looked like, actually, that magenta line. You can see the spiral. So this is a 2D plot, but you might imagine that it's spiraling down. So we go into the eye and spiral from 10,000 feet and get down to about 5,000 feet. And then we went out. Too bad we didn't go out to the west. There was some logistical reasons we couldn't do that. And we circled around, and now we're in the eye wall. And we were just heading down to where the sail drone was, but we got pretty close. So I give us a B- for this, for considering how tough it was. Next slide, please. Okay, so we also flew other things. The S0 is a much smaller drone. The Altius is about 27 pounds. This is 3 pounds. So it's really small. Still measures the same thing. Both of them have turbulence probes on here too. I should mention, George is going to be talking about LES modeling and things that we want to get on the really small scale. And these types of observations will allow us to do that, and we'll explicitly get UVW. Next slide, please. So it's a little small here, but it's we have altitude with time. And this just shows towards the end of the flight there where it says zoom. We're down to 60 meters, and then the last leg is down to 20 meters. And this is in about 50 knots of wind. The little blue dots are lasers. So we have a laser pointing down, so it can give us some, we want to make sure we don't hit a wave, but we also can use that for maybe to pull out the spectra of the wave later and to see some of the wave dynamics. You can see as it went into the ocean there, at the very right lower part, you can see we got down to measurements as low as 3.5 meters above the water. So this is the kind of observations, really small scales that will help us as the modeling community keeps getting smaller and smaller scales, and we're looking at turbulent quantities that we want to quantify and parameterize. This is the type of data that we think can help. Next slide, please. I won't spend a lot of time on this, but this is a little bit of we're using AI too. So we don't just say, hey, go do a 20 nautical mile radius around there and orbit in the storm. This is a wind finding algorithm for the S0. No, we were not flying a Tesla, but just Cessna, but you definitely not flying a Tesla, although he launched one into space, didn't he? So this is basically, just think of this as that S0, and what's happening at the end there, and I'm getting into it, you can see it's pretty stable at first, but then it's actually tracking the wind. So every 5-degree wind change, it's changing. So we got to put a low pass filter on there so it wouldn't go, but these are the types of things you learn when the first time you fly in a storm. So it survived when it really probably shouldn't have, because it was constantly turning and flipping over, but still flying. So very actually encouraged by that. Next slide. So Sky4, I want to mention the last bit I'll talk about. These are 15-gram dropsondes, half an ounce. We have different versions that we can create. Today we're going to talk about the basic version, but we can create them so that they're heavier, so they give us a more vertical profile, or much lighter, and think of like a twister where they're staying up for maybe a long time, maybe even an hour. As it is now, the standard one falls half the fall speed, about 5 meters per second, which is the dropson, I believe, is about 11 meters per second. So we're basically getting twice the amount of data for, you know, the period that it's up there. Up in the right corner, we dropped 8 at once. In the near future, we hope to be able to drop 50 at once and be able to just have them floating around, falling around. So next slide, please. This is just a visualization that Sky4 gave me. So you can see this is temperature. You can just see out of the 8 that we dropped, we also dropped the dropson in the next visual I'll show you here. And yeah, I'm probably getting closer, but I'm close. So you can see the temperature is increasing as it's going down, which is nice. It actually worked. Next slide, please. And this will take about a minute, but it looks like nothing there, but you'll see there are going to be 8 different trajectories. The first one that's jumping out on the left there, that actually is a dropson because it's falling faster. But you can see the other 7 streamsons that were released in rapid fire as we were flying through the P3. So this is just a visualization to see like what it might look like. I think the ocean might be a tad more violent than it is here. But besides that, this is a pretty good idea of what you're seeing. And you can see it also, the trajectories are different too because it's falling faster. The form factors are different. These can also measure sea surface temperature in addition to PTH and winds. So that's all I have.
We do have a little bit of a buffer, so if you want to let the image run over.
Okay. Yeah, it'll take about another 30 seconds or so. But you can see that the dropson is, the purple line is out ahead, and it's in the water already. So the others are just, you know, keep going, and you can see sort of the spread between them. But very, very exciting technology. Since I have a minute, I'll say we are planning to do more testing for these 3 systems. We also are going to be looking at something called land launch. Everything has been from the plane. We're doing a land launch UAS, which can stay up to 20 hours. So this thing is going back to the roots of the people who know me a long time. With the first time we dropped UAS back in 2005 with the Aerosonde. So we're trying to visit that. They're cheaper. They're better technology than they were 20 years ago. And we're also going to, as I said, test more with the Streamsonde and maybe that 50 drop at one time capability. So that's kind of what's coming in the future. More of this and a little bit more that I haven't shown you today.
Give us 1 second to switch back to those.
Okay, while you're switching, I'll just introduce George. George Bryan from NCAR will be giving our next talk here. And George and I are sitting together, well, not exactly together, but on the same building there. I'm sitting with NCAR these days out in Boulder. So George and I have known each other for quite a long time. And you know, the scales he's on, I think, match well with the observations that we're trying to look at to see what the impacts are for modeling.
I think we're going to have to move the slides for you because the being a little wonky.
And one last thing I'll say, George is doing a year-long sabbatical with HRD this year.
Oh, hold on. Sorry.
Working on LES modeling in the operational system to see how we can expand that.
Thanks, Joe. Yeah, I'm George, and this is actually the first HFIP annual meeting I've attended. So I'm learning a lot here. I actually attended some HFIP monthly science meetings way back in the day. Gopal reminded me of that, but this is the first annual meeting I've attended. Okay, so what I'm going to talk about is some model observation synthesis using some large eddy simulations of hurricanes. So next, please. In case you don't know what large eddy simulation is, it's basically you just integrate the governing equations with sufficient resolution that you can resolve the turbulence, what I call eddy resolving resolution. You need grid spacing, depends on the problem, but around 100 meters or less in terms of horizontal grid spacing. And the key here is you don't use any boundary layer parameterization. You don't need to parameterize the effects of the turbulence if you actually are resolving the turbulence. So there's a image down here at the bottom. It's a 3D visualization of a daytime sunny boundary layer from Encyclopedia of Atmospheric Sciences, a nice review article if you want to catch up on what large eddy simulation is. And one of the reasons, there's many reasons we do this. You can do some diagnostics, like in the bottom right here is an example of a heat flux profile. And you can see that negative heat flux at the top of the boundary is really hard to parameterize in PBL models. And it's also very computationally expensive. This is why this isn't going to be run in real time very soon. There's some possibilities actually for that with GPU. But I'm doing this mostly for research modes. And you'll see some of the applications we've done in recent years in some of the upcoming slides. So next. I won't go into too much of the details. I ran this simulation like 6-7 years ago. It's a idealized tropical cyclone in no flow and no shear. It just sits there and spins in the middle of the domain at maximum possible intensity. The goal was to simulate a relatively small storm that would fit in this 80 by 80 kilometer box where we have high resolution. And these are simulations with 31 meter horizontal grid spacing, 15 meter vertical grid spacing. The numerical model is CM1. It's a model I've been toying with for the last 20 years, and it's pretty good at these kind of simulations. Doesn't cost too much, and you can run really big grids. So next slide, please. So here's what it looks like. This is kind of zoomed in on the north side of the eye wall. This is an animation. I'm surprised it worked. Most animations don't work for me. This is 10 meter wind speed. And you can see the eye where all the blues and green colors is. And then there's this very sharp transition to the eye wall. And you can see the reds are 90 plus meters per second. If you're really close, you might be able to see the black contours, which are encircle 100 meter per second. Instantaneous wind speeds, all kinds of structure and detail. So this is what might actually be out there in nature if this is a realistic simulation, a realistic depiction of the atmosphere. Next slide, please. This is just an instantaneous snapshot of one time, and you can see the scale of a lot of these structures is a little less than 1 kilometer. So yeah, you need 100 meter grid spacing or less to resolve these kilometer scale structures. Next slide. And this is what the 10-minute average wind speed looks like. This is what NHC, I believe, cares most about, sort of a time average or spatially average wind speed. And so you can see the maximum value is 71 meters per second. So just barely into category 5. And could you step backward one slide again? And just to show again what large eddy simulation buys you, you get how much more detail, of course. Forward, please, and next slide. Okay, one of the things we've done is we've looked at wind gusts. You may be familiar with this case, Tropical Cyclone Olivia in the made landfall on the northwest coast of Australia in 1996. It set what was, at least as of 10 years ago, the strongest surface wind gust ever observed. There was like a 10-meter tower on this island off the coast of Australia. They measured 113 meters per second wind. One of the big controversies about this was the gust factor. If you take the peak gust divided by the mean wind, that's at 10 meters, it's usually around 1.4 is kind of a good rule of thumb. Gust factor was 2.7 for this case, which some people said, well, that sounds unrealistic, must be instrument error. But if you go into the next slide, this is analysis. There's a couple things on here. The contours are the mean wind speed in this radius height analysis space. And the shading, though, shows gust factors, the maximum 3-second gust divided by the, I think it's a 10-minute mean. And so you can see the 1.4 is right about where the yellow starts. And so you can see outside of the RMW, beyond 12 kilometers, yeah, you get 1.4 down near the surface. But look in this eye wall interface, this kind of transition between the eye, where things are calmer, more solid body rotation, and the eye wall, where you have this massively ascending air. You get gust factor above a value of 2 in the simulation. So we think that that gust that was measured on Barrow Island in Australia is probably analogous to these small-scale gusts we see in these simulations. Next slide. Nice analysis done by Dan Stern. I won't talk about the left slide too much, but that shows kind of a time series of the different averaging periods. So 75, 76, 77 is the average wind, and the peak, though, in the model is going up over 120 meters per second. People's like, what's that about? There must be something wrong with your model. Well, we think these structures may actually exist. And Dan did this nice analysis. So on the right, we actually ran, during the model run, integrated every time step in the model run, 100,000 drop signs. So yeah, 50 stream signs would be great, Joe, but try doing 100,000 drop signs, haha. Simulated drop signs, of course. You can look at the paper for more details, but only a really small fraction of those drop signs measured these 110 meter per second wind gusts. So it's they're so small and they're hard to capture with a lot of conventional technology. So next slide. And this is an example showing about analysis of Hurricane Andrew. So Roger Wakamoto flew some planes over the damage right after the storm passed Homestead, just south of here, and noticed some swaths, some tornado-like swaths embedded in what was otherwise comparatively lower wind speeds. So Roger said this is most likely a tornado-like vortex embedded within a hurricane. That's kind of what we're seeing in our simulations too. So we think these are realistic structures. Next slide. And this is showing, Dan found these images. This is vertical velocity as retrieved from the dropsondes. And the left is an actual observed dropsonde sounding from a very turbulent, intense storm. And on the right is a simulated dropsonde profile. Eerily similar. So again, we think the simulation is doing some right things, we hope. Next slide. Okay, getting a bit more quantitative. This is a study done by Xiaoming Chen, now at University of Alabama, Huntsville. On the left, the colored lines, so the black and the green and the orange are from actual model output. This is the vertical momentum flux, non-dimensionalized by the average wind speed at each level. And all the dots are various observations over the year, going back to Sea Blast in the gray dots to the Coyote UAS that Joe flew in Hurricanes Maria and Michael. And that's C20. The red dots are from CO in 2020, the BAMS article. And on the right is analysis of effective length scale, turbulence length scale. And from these numerical simulations, which are again in the colored lines, we were able to make some adjustments in the HAFS model. I think it actually went into HAFS B this year. You can talk to maybe Andy about exactly what went into the modeling system. Next slide. Okay, real quick. So this is the exact same data Joe sent you. These are I believe there were 8 stream sondes. So thanks to Joe and Josh Wadler for forwarding me these are the trajectories of those eight stream sondes launched about 1 kilometer apart. Next slide. So Joe had this in the corner of one of his slides. This is the wind speed of these 8 stream sondes from Hurricane Nigel. Pretty similar. You can immediately see, yeah, hurricanes are really turbulent. You get a sense of the variance in the winds. This is why we might want to drop a whole bunch of stream sondes at once to get some turbulence parameters we can use to evaluate the boundary layer model. So I have 2 more slides. Next slide. Okay, on the left is Joe's Hurricane Nigel observations. On the right, I decided to do some simulated stream sondes in this model simulation. And there's like 10 trajectories launched 1 kilometer apart. Now we get a much smaller storm, so you can see them sweep around the storm really quickly. And then next slide is the last one. So there's the stream sonde actual observations to the left. On the right is a whole bunch of really noisy, really turbulent data. Very qualitatively similar, but we want to use these simulations to help us decide how do we configure the stream sondes to get the data we want? Do we have to have different fall velocities? You can shape the stream sonde shape so they fall a little bit lighter, like Joe said. Where do we release them from? The model gives us a little bit of a test bed to try things out before we go into the field. So this is blue sky ideas here. And then the next slide is just a summary. Not even a summary. There's my email address and there's the CM1 webpage. You can find some of the links to these papers. Thank you very much.
Well, George left us with 30 seconds. So I have to say that was definitely not recycling old stuff. That was like literally just did that probably last night in your room, I'm sure. So our next, Jim Doyle's next. Actually, yeah, I guess we switch that. Jim, are you ready to go?
I'm ready to go. Can you hear me?
Yes, we can. Jump right in.
Okay, thanks, Joe. So I'd like to acknowledge my co-authors, Jason Dunyan, Rob Rogers, John Moskaitis, and Josh Hossuth, who's at ONR, as well as the TCRI team. So this is an overview of the Tropical Cyclone Rapid Intensification Program that we've had the last several years working with ONR and HRD. Next, please. So the focus of the ONR program is to identify key processes and predictability barriers governing RI, with a lot of focus on the onset of RI, as well as boundary layer and cloud microphysics processes. We've worked in close coordination with IFEX and AFEX through this program. And this just shows a nice graphic from John Moskaitis, a performance diagram showing a storm-by-storm comparison for the Atlantic from 2020 to 2022. We haven't updated it yet for 23. And there are a class of storms for COAM's TC, as well as other models like HWRF and HMON, where the RI forecasts for storms are actually quite good. A prolonged period of RI, typically peak intensity is rather strong, Cat 4 or above, medium to large inner cores, the models seem to do quite well on. And then there's another class of storms, CTCX and other dynamic models seem to struggle with, and these include storms like Delta and Sam. Last year, both had small inner cores during RI. Some of them had complicated shear. patterns, which was true of Delta. Next, please. So we've, as I mentioned, worked very closely with Jason and Rob and the team and Heather with NOAA AFEX, and we've been adding P3 flight hours, extra dropsons on the P3 and G4. And you can see through the years from 2020, we've contributed to observing a lot of storms and added a lot of extra dropsons. In 23 in particular, we've added SONs on flights from Franklin, Adelia, Lee, Nigel, and Tammy, and also performed 6 microphysics spirals as part of that. There's some graphics on the right showing some of the nice TDR diagnostics coming from the P3 for Hurricane Adelia. Next, please. And Jason very nicely provided an overview of the capabilities in terms of instruments on board the P3. And just to highlight a few, of course, the TDR is extremely important and brings a lot of information together. And the cloud imaging probe that Jason talked about, extremely important to our program. And Michael Bell and his team have been analyzing a lot of that data. Last year, we had the compact rotational Raman LiDAR available, and other instruments like the WSRA that was on the P3 throughout this program, and of course dropsons. And we also released quite a few AXPTs, many of them ONR based AXPTs. Next, please. And we contributed a lot to various flight modules in this program, and this is just an example of a flight module that Dan Stern conceived. And this is the flight level assessment of intensification and moderate shear, or the FLAMES module. It just shows it's basically designed to repeatedly sample the region of maximum winds at an asymmetrically intensifying TC. So instead of turning downwind at the end of an outbound leg, the plane returns back inbound and flies along the same azimuth. And the FLAMES module was flown on a number of missions in the past year. Shows an example on the right for Franklin. Next, please. I mentioned microphysics. Michael Bell and his team have been analyzing some of this data. There's a lot to unpack on this slide. In the upper left, it shows, this example is from Ida last year. You can see these spirals that the P3 flew, flying up through some stratiform regions and getting really good measurements with the probe of the microphysics distributions. And I think what they are finding, which I think is really interesting, is high concentrations of pristine ice, possibly rimed ice, but especially interesting are the high frequency of graupel and aggregates that really dominate the distribution greater than a millimeter, which is quite interesting since this is generally stratiform regions. So there must be some graupel that is being transported laterally from the stronger convection in the inner core or some of the rain bands. Next, please. So at the AOML team, Rob and Michael Fisher and others have been using composites of the airborne TDR to deduce relationships between the structure of the storm and intensity change, including RI. This is some work that Michael has led in 2022, that appeared in 2022, and they found little relationship between the tilt and the future intensity change for strong TCs, but tilt is a really good predictor for intensity change for weak TCs, with a small tilt being necessary but not sufficient indicator of RI. Next, please. And then a follow-on study that Michael led looked at, once again, this characterization of intensification of these storms using the TDR data set, and found that intensifying TCs concentrated in the low tilt, low ventilation region of parameter space. So the RI cases mostly occur where the tilt is relatively small and the ventilation is relatively weak. And so it just highlights the real importance of the sort of multi-scale kinematic and thermodynamic processes that need to take place to sort of kick off this onset of RI. Next, please. Just to mention, we had a summer student, Nicholas Johnson from University of Albany last year, working with John Moskaitis and myself. And Nicholas did some very nice work on the Hurricane Delta, which is a really complicated case in 2020, which was one of the TCRI storms. And he looked at both the weakening and intensifying phase and found some very interesting patterns. He was looking especially at aspects of ventilation in this storm, and he found weaker vertical wind when the storm was intensifying with a larger area of upward motion relative to the weakening phase, which had more intense upward and downward motion in Delta. And then he did some nice comparisons between COAMPS TC and the TDR data for this case. And that generally they had broad similarities between the two. Next, please. So just summarizing the ONR TCRI program, I think the observational and modeling studies, which I haven't really talked about, highlight really the complex processes related to boundary layer microphysics in the environment, including the tilt that is becoming very apparent as an important precursor to rapid intensification. So the next phase for the team is really concentrating on research and publications, but ONR is supporting a smaller team involving NRL and the NOAA HRD to have continuing ongoing collaborations. And we're continuing this past year of supporting, as I mentioned, additional observations and flight modules, and also building on this research relationship amongst the team, along with some of the ONR investigators to continue to look at the RI problem. So ONR will continue to collaborate with HRD and AFEX. And then as Jason mentioned, there's also a synergy with the MAGPIE program that's centered on Barbados, and there may be some additional P3 flights next year related to that program, focusing on some of the boundary layer processes along with the Navy Twin Otter. And I'll stop there. Thank you.
Thank you, Jim. I'd just like to add about the MAGPIE, potentially next summer, we may also be able to test some new technology, that land-launched UAS. We can get some data validation out there too. That's one of our hopes. So moving along here, we have Greg Foltz from AOML. We'll talk about what he did and what his team did in the past year with Saildrone and in support of the CHAOS program that was funded by COMO.
All right, thank you, Joe. So I'll talk about some coordinated ocean atmosphere observations that we did during the past hurricane season, and we call it CHAOS for short, so Coordinated Hurricane Atmosphere Ocean Sampling. And this was the first time we had done this, first time we'd attempted such a coordinated campaign like this, and it turned out pretty well. So it was supported in part by NOAA's Global Ocean Monitoring and Observing program, GOMO. And actually Cheyenne Steenbarger was planning to give this talk and she couldn't make it, so I'm kind of filling in for her as one of the co-investigators on CHAOS. Next, please, or can I?
The remote deck. So
okay, all right, excellent, thanks. All right, so this CHAOS program is kind of embedded in a bigger program within NOAA GOMO called the Extreme Events Program, and this has been going on for a few years now. And the idea is, so I there are a few points here. So if we start in the upper left, we want to bring together experts from different disciplines. So ideally from the ocean, the atmosphere, and the air-sea interface, covering the whole air-sea transition zone, and different line offices, operational, research, cooperative institutes, academic. And another big part is to bring together the observing and the modeling communities to try to see how the observations can help the models and where observations are most useful. So if we look down on the bottom, another key is that there was no funding for this program initially, so we really had to leverage what was already happening, what was already funded in terms of observations. That changed last year with some money for this CHAOS program, which I'll talk about in the next slide. Okay. So that the last thing there is to coordinate ocean observations, and the ultimate goal is to improve models, improve forecasts. So we want to try to get data co-located, coordinated to see if we can do that. All right, now you can go to the next. All right, so the funding, kind of a one-time funding of $2 million went to GOMO, and this was used to fund the CHAOS program for this past hurricane season, and it funded 8 different projects. I'll summarize some of these in the next couple slides, including 7 early career scientists as leads and co-leads, and more than 20 partners collaborating in this. And you can see some of those logos there on the right, kind of separated into NOAA on the top, and then other academic and other partners on the bottom, including HFIP on the bottom right. So next slide. So a summary of kind of what we accomplished during the hurricane season for the CHAOS campaign. We had, I think we had pretty good success, everything considered. 4 hurricanes, main hurricanes that we got coordinated observations in, and those were Idalia, Lee, Nigel, and Tammy. And so first, the expendables and remote sensing. We had 5 A-sized drifters, so these measure the wave spectra from the surface drifters. Those were funded by this program, deployed from the P3s into different hurricanes. 40 drop-sons funded by this, and those were also deployed from the P3s. What Joe talked about, we had 4 uncrewed aircraft systems that were deployed. I'll talk a little bit about that. And numerous overflies of the P3s with other observations in the ocean, drifters and sail drones, mostly getting co-located data to compare and validate between the different observing platforms. And in situ observations, these were also funded partially by this CHAOS program. So we had gliders. So gliders normally don't have ADCPs, so they can't measure the profiles of the ocean currents. This funded 2 of those gliders to put ADCPs and get profiles of currents, and 5 rapid cycling Artigo floats. These are in the Western Caribbean, and they profile every 5 days instead of 10 days, which is the normal. So that helps, especially ahead of hurricanes, getting more profiles. And 19 unique, as Jason mentioned earlier, 19 unique sail drone hurricane and tropical storm encounters, and they measured, I think, a max sustained wind in those hurricanes of about 70 knots and gusts of more than 90 knots. So next slide. All right, so I'll go into a little bit of detail on the different observations and the different coordinations that we did during this CHAOS program. So the gliders and sail drones, you can see them there in blue and red, and we had good success coordinating the sail drones with the gliders. You can see some overlap there between the red and the blue. In terms of getting co-located data in hurricanes, not so successful, and that's just because mainly the gliders like to hang out near the coast, near land, and in this hurricane season, we didn't have a lot of tropical cyclones that went near the land, and that's good, of course, but it means that we don't have co-located data in hurricanes, which we'd like to do. So maybe we can get more gliders offshore. That would be, to me, the best solution for that. But anyway, but we had a lot of good coordination. And I'll point out one thing. For the first time, we had co-located data from a sail drone and measuring the surface atmosphere and the ocean, and an ADCP measuring ocean currents, and a glider that had an ADCP on it. So we get like a comparison of the ocean current profiles. The first time we had been able to do that. That'll be good for validating and looking at the currents. So next slide, please. All right, Joe mentioned this. I'll just go through it quickly. We've been trying to do this for a few years. It had been a goal of ours, at least for a few years. And so we're finally able to do it last year, thanks to a lot of different coordination, a lot of messages back and forth, figuring out exactly where the sail drone was and coordinating with the P3 and all that. So that was fun. And so we got the sail drone about 10 miles. The uncrewed aircraft system, UAS, was deployed about 10 miles from the sail drone. You can see the sail drone there, and the pink line there is what Joe showed, the kind of the spiraling there. And we also had 3 overflies of the P3 over the sail drone, dropping sondes. So IR sonde, normal sonde, and AXPT, all deployed within about 10 miles of the sail drone near the Altius. So that was a good success. And there were actually 4 UAS deployed in that Hurricane Tammy. And they were actually near the eye wall. This was a sheared storm, so that convection, the IR image there where it's strongest, that's actually kind of where the eye wall was. So it was good, turned out very well. And we get co-located winds, temperature, pressure, and humidity from these. Next. So waves, we had significant wave height measured from different platforms, from the P3s, the altimeter on the P3, and winds from the IRAP. And so in this case, on the left plot on the left, you can see the southernmost P3 track there, and the colors on that track are the wave height, significant wave height in feet. And we had a sail drone there in the southern part of that track. So we got actually pretty good co-located data between the wave height from the P3 and the sail drone, which would be good. And comparisons so far look pretty good in the wave data. And on the right, those were surface drifters that were deployed in, this was Nigel. So there's one, the small white dots show where the drifters were deployed in the eye of Nigel on the top right, and then kind of in the northern eye wall on the bottom plot there. And again, the colors are the P3 altimeter significant wave height values. Next. GeoCollaborate. So Dave is going to talk about this in his presentation next, I believe, but I'll just summarize it briefly. So this is a useful tool. So it gives a visualization and helps with coordination of all the ocean observations, especially that we have during the hurricane season. So near real-time updates of positions, and you can see the data from them coming in. So that's very useful. And the P3 tracks, the plan tracks and the actual tracks when they're happening were updated, so we could see all the co-location of all the data. And some of the data from the P3s was uploaded in real time. So this was a really useful planning and tool for coordination during this project. And I think that's all I want to say. Dave will say more about this next. All right, so finally, of course, we want this data to help models and improve forecasts. So that's a big part of this program, and there's funding for this. And Hyun Suk earlier today talked about some of the work she's doing with other scientists at AOML and CMIS to make progress on looking at the data in the models and doing OSEs, withholding data, and see how it impacts the forecasts. So that's a big goal. And I just took, it's still underway for this hurricane season. We don't really have any concrete results yet to show. So I showed an example here from Hurricane Michael, just showing the importance of ocean observations. If you look at the curves there where no ocean data or just the climatology is used, the dark blue and the light blue, you can see it really underestimated the intensity of Hurricane Michael. And then if you include the actual ocean conditions in the red, assimilating the ocean data does much better, capturing pretty well the intensification of Hurricane Michael. So I will end with that. Next slide. I just want to thank, well, I especially want to thank Cheyenne, the program manager who did all this, and the P3 flight crew and the scientists, especially Jason and June, who really helped coordinating the flight data with everything else, and all the PIs on the project. So thanks, everybody. And end with that.
Thank you, Greg. Our last speaker before we have our discussion afterwards will be Dave Jones, and looks like he is getting ready and he's sharing his screen. Dave, are you ready to roll?
Yep, just had to unmute there. Can you hear me okay?
Absolutely. Sound good.
Okay,
Take it over.
great. Okay, thanks so much. Well, thanks for having me speak here. I'm going to be talking about how we supported the NOAA Chaos Hurricane Field Campaign with GeoCollaborate. So the use of GeoCollaborate within Chaos is intended to see how a real-time collaborative environment can improve coordination efficiencies, situational awareness, and decision-making. And I'd like to just give a big special thanks to Jason Dunyan and the HRD team for their willingness to help with and use GeoCollaborate across the partnership. And also to Joe Sapp from NOAA NESDA STAR for generating data services that were incredibly valuable during this field campaign. So I just want to give everybody a quick overview. What is GeoCollaborate? Well, we all know there are a lot of data portals, websites, and hubs out there that have great data that are offering it out. But there's no one place to get that information. So what GeoCollaborate does is it reaches into those portals, websites, and hubs and pulls out the data and puts it into what we call a collaborative common operating picture, or CCOP. And then this is how it looks. You have a leader that can log in with credentials. They can add data into it, turn it on and off with on-off switches, and then any followers in the upper right-hand corner can connect to the same URL and turn GeoCollaborate on. And all of a sudden, you're connected into a real-time collaborative environment with the leader. It's a geospatial data sharing collaboration environment, so it's not screen sharing. And then down the bottom, you have this collaborative dashboard that's operating 24/7, 365 with all of the data sets that the leader has activated for everybody to see. And they can make queries on that data as well. So I'm briefly going to discuss 6 innovations that we brought to the CHAOS field campaign. Overall situational awareness, this is the GeoCollaborate dashboard. So we had flight plans that we could input. We had planning. Some of the planning of the flight plans happened using GeoCollaborate. We had live flight tracking. That's what this blue line is. You can see the live flight when the P3 ferried down to Barbados to fly into Tammy. The position of ocean obs assets, NESDA satellite imagery. We were bringing in the sandwich sector, the sandwich product from the Meso 1 sector from Goes East. That was updating every minute or so, every 5 minutes occasionally. And then we had the NHC forecast, so we could see the official forecast, track and intensity, and what ocean observation platforms are likely to be impacted. And then we had key points updated frequently. So we updated this during the missions, kind of like a one-way chat, showing the status of things going on and instruments and things like that. This is an example of the Argo floats that were available too. And the cool thing about that is you can click on each Argo float and see when it last surfaced and reported and when the next expected report was going to be. This is really important for coordinating coincident drops if there was going to be any Argo floats that were coming up. The second innovation is this aircraft tracking, drops on release and track at pre-splash hubs. This was fabulous. I look forward to this every time we had missions went up. Here's an example of N43. This is for Tammy. Might be the situation that Greg was talking about just a few minutes ago, where the plane is flying along this path here, and then it dropped a sonde. You can see the track of the sonde, and then the observation here is the last observation prior to splash. So then N43 came down, made a turnaround, came back on this return leg, dropped another sonde. You can see the path it took and the last observation before splash. Another one over here, and this one that looks like it didn't have much of a path because it was close to a center drop, which is pretty awesome in itself. These dots are sail drone positions at different times, and I'll get to that with another innovation here. Innovation number 3 was flight plan and coincident measurement planning. So I was given an account on NASA's MTS, the Mission Tool Suite system, when Jason would upload the points for the flight plans, it would automatically create the KML. We could bring that immediately into GeoCollaborate and then across the dashboard in real time. So everybody could see the flight plans and where the plan drops were close to any ocean observing system. So this puts all participants across all line offices seeing the flight plan automatically and assessing coincident drops interactively. Innovation number 4 was the WSRA and Kaya data visualizations and drifter measurements. I think Greg showed this as well, but as soon as this A-size DWSD was dropped in the eye wall of Nigel, which incredible 70 to 75 mile wide eye, it turned on in 20 to 25 minutes and we were getting the data. And so you could see the passes with WSRA over the sensor. And there were more after this screen grab was taken. And then the next day, another one was dropped to the northeast of the eye wall in, this is Nigel. And you could see both aircraft were flying at the same time. This is pretty awesome. This is the WSRA, and then the Kaya sensor was grabbing both significant wave height estimates with the real-time DWSD drifter reporting back those obs too. So really terrific. I'm going to go back to innovation number 2, add a little bit of measurement here. So this is really great with N43 dropping this sonde at 1559 Z. It splashed, or the last observation prior to splash was a 1602 Z. You can see this ob here, 13.75 meter altitude, a 24.7 meter per second horizontal wind was measured, 1602 Z. Well, it fell 4.2 miles from sail drone 1040, and 1040's observation at that exact same time, 19.38 meters per second. So in less than a 5-mile distance, we had about a 5 meter per second or so difference in the observation, and this was much higher. So this was really exciting to see, and see it in near real time. Innovation number 6 was WSRA Interactive. You can see all these returns coming in near real time from the aircraft, bringing the with the WSRA showing the estimated significant wave heights. And then I got the KML file from Ivan at ProSensing after the mission, overlaid directly on each one of these observations, which made it interactive. So this is an 11-foot estimated significant wave height, and that was very exciting too. In the background is the Meso 1 sector sandwich product, so we could really see the convective tops there and some of the overshooting tops. Now, we did have some challenges. The first challenge was direct access to the sail drone data feed. We didn't have one. It would be great to have that network KML feed directly from sail drone, which would make a huge difference for ensuring coincident observations. Currently, we're getting it from ERDAP. That had about a 2-hour delay, so made it a little bit tough for planes that were in the air, because I had the access through MTS to be able to chat with the plane live, and it was a little bit tough given a 2-hour delay with the ERDAP data. Accessing AXBT and XBT data, hopefully that can be easier. Currently, it's right now in the GTS. And easily determining which Argo floats would be surfacing near any missions to coordinate planned drops. I've already talked to Woods Hole Oceanographic Institute and Pell Robbins. She said, hey, you know, we could make these Argo floats maybe different colors or maybe different sizes if they're going to come up in the next 12 hours or the next 24 hours, which could make it really an easy visualization to see when you're planning coincident drops. And then the aircraft bandwidth was a challenge, but as that's addressed in the future, GeoCollaborate could be used live on the planes to see where all these platforms are in real time, and they could make plans accordingly. So where do we see this going? Well, I would love to expand the cross-line office collaboration, getting GeoCollaborate into the HOT, the Hurricane Ocean test bed. The mission of the HOT is very similar to what GeoCollaborate can deliver. We are cloud-based collaboration, trusted data sharing environment. We already have partners throughout NOAA involved, and I would really love to see early career professional engagement in this real-time data collaboration environment. Everybody we've shown it to within NOAA and over at NASA as well has said, boy, this is really a great environment. Also, the integration of model forecasts for collaborative parameter validation and verification, bring model data in there, validated immediately with the real-time obs could be really spectacular. And then integrating GC into Cesium for a collaborative 3D environment. This would be spectacular. Cesium has a 3D visualization engine built right into it, and integrating GeoCollaborate into that would provide, really bring that 3D data alive. And then connecting GC to Doris for sharing any past storm and associated data across line offices. Doris, I got a demo of that several weeks ago from HRD and AOML. I can just imagine bringing in historical hurricane data and tracks and information, and then sharing that out live with groups and private sector operators like communications and emergency managers and things like that, showing what the impacts were from historical storms could be really very powerful. So that's my presentation. You can scan the QR code or download the presentation later. There's a 4-minute video describing what we did for chaos. And that's it for me. Thanks so much for your attention.
Question here, and maybe we're going to have some discussion. Not maybe, we will have some discussion. So the floor is open for any of the speakers, or I don't even want to go broader to just observations in general to see, you know, how these innovative observations and the routine observations too are making a difference for the operational modeling system and where we're going with that. So
That's what we're doing.
yeah, so what do we have here?
Joe, there was a question from Pete Black. Yeah, Funny, I was thinking the same thing. So what Pete had asked a while back while you were talking was about the slow fall rate of 5 meters per second. Those won't be very vertical in their profile, correct? As in slant-wise profiles. So it seems like you would need your 50 SON or more cluster to retrieve anything like a vertical profile. Is that your intention? And have you looked at other? He later on went to ask about looking at other fall rates being used simultaneously.
Well, Pete, bottom line is we can someone, if you mute your mic there, if you're not talking, please. So bottom line is we can never really get vertical profiles using drop sons. And at times we want that. So we're working with how we can potentially do that by adding some mass, looking at different ways these things fall. They don't use a parachute. We had some issues initially with they were spinning pretty badly when we first tested them in March. But that's why we do the testing in clear air, and we put a stabilizer on there. So we kind of took a step back and said, let's not look at that quite yet. But we're open to ideas. I think the two real models that we want to look at are, can we get a vertical profile, and can we have it, dirty it up, if you will, and have it stay up sort of like, the Twister movies or like Chaff, where it's just up there for a really long time, and just look at what's the impact of the data coverage and what's the impact for data assimilation. But
you might need to move out of that spot. You're right between the two speakers, so we're getting feedback.
am I going to get cancer?
I hope not.
Oh, okay.
Because if you do, I'm screwed because I'm between those things all the
I don't
time.
want to get bombarded with radiation. So that's the end of that question. Did that answer it, Pete?
Yes, Joe. I think you got a lot of potential avenues to follow there. It's great.
Yeah,
Jason.
sure. So I got a question / comment for George Bryan. I have been dying for years. I've talked to a lot of people about this. I would love to see a more thorough examination of simulated reconnaissance data taken through your simulation, and exploring some of the assumptions that are made. For example, with drop sons. And one example that comes to my mind is, what does WL150 mean, right? And how does that relate to Vmax? Stuff that we do in operations that it has some basis, right? But you can do only so much with real observations, and we really need something on the other side where we have almost unlimited capacity to look at this through a simulation like yours. And I think that's really ripe for a lot of research.
Yeah, thanks, Jason. And I agree. There's a lot of cool research and insightful diagnostics that can be done with simulations like this. I remember Dan Stern actually did a comparison of what's it called again, WS150 or WL150, winds averaged over the lowest 150 meters or something like that. So I don't remember now if that made the paper or not, but I know he presented it maybe at the meeting, Hurricanes meeting that was in San Juan, or you can just email Dan. He can show you some of those results. Yeah, so there's a lot of fun stuff you can do, and I'll add, so not only does this high resolution help you with all the turbulent structures, but I think if you want to do this well, you have to simulate the paths of the observing systems in the simulation every model time step. So we actually did simulated drop. We got the equation for the fall speed of a drop zone and added it as trajectories into the model. The same thing with I have flight level data where you're translating a mock airplane every time step in the model. The problem with that is you can't simulate the actual ups and downs of the plane because you don't know how the pilots are going to react to individual gusts. So, but it's pretty close. We just fly the plane like straight and level or something like that, and hope the comparison is really good. And same thing with the UASs and the stream sons. And if anyone else has anything else they want to fly through the hurricane simulation, please let me know. We'll give it a try.
And you could really, you could do a whole paper just on this kind of stuff.
Yeah.
My comment was you could really do a whole paper just on this kind of operationally oriented stuff that I think it would be really worthwhile. I mean, if you said he did WL 150, great. I think that kind of stuff, it needs to be written down somewhere and published because, you know, this is kind of stuff we really need to reference back to at some point. We don't really have, you know, we don't have a lot of documentation on stuff like that, at least, you know, from that kind of standpoint.
Don't forget, Jason, that the 150 is just
is available for anybody.
just a guess for the depth of the boundary layer. It varies quite a bit. It can vary from 50 to 200 meters.
Yeah. Okay, so I was looking at Joe's data sets from the UAVs and so forth, the US, and looking a little futuristically. I'm going to try and show tomorrow in my talk, but it's 10 minutes. I don't know how much I'll have. But we are actually using generative AI to create some synthetic data for buildings, and then importing that data into models as if this was a real observation. And that way, the model actually gets parameters it doesn't have. Looking at all the data, I'm wondering if anyone has tried generative images for hurricanes and then try to read them as actual LiDAR or some other imagery within the model, and whether anyone's working on that.
Does anybody want to tackle that? Anyone working on some AI generative stuff or even machine learning? I think it's a great idea, but you know, I just not in my wheelhouse.
It's very promising, and what we saw with the urban thunderstorms is that it's almost like a real observation, but in a theater environment. So if you can realistically create the hurricane, I think there's an ability to extract that information back into the model, is what I'm trying to convey. And a little bit of research, and we could probably get some lot of exciting data just into the future.
Frank?
Yeah, so this is for Stephanie's talk. You were talking about all the different estimates you get, and then you listen to what George is showing. Maybe they're all right. What does the peak wind mean? I mean, it really begs the question, why are we hung up on this peak wind and not looking at something that we actually can measure, like radius or area of wind coverage by certain speeds? I mean, it just speaks to the uncertainty. I remember, Chris, you did a paper for us on what the hurricane specialists thought the uncertainty in the peak wind was.
Well,
and we have all these definitions, WL 150, surface, flight level, SFMR. Maybe they're all right.
yeah, you know, Frank, let me follow up on that. So as we're getting into these like really, really high resolution observations, and it's nice because it's matching up with the really high resolution modeling that we're all looking at too. Those stream sondes really come back to, in George's talk too, it's the plot where you said where you smoothed it out and it was 71 meters per second, and then you backed out and showed it's like, you know, pulling away the curtain there. And I just wonder if some of the definitions of what we're using as verification are just because the technology or the ability there wasn't there to look at this sort of thing. But that shouldn't stop us from saying, well, okay, now that we open that door, do we need to verify that? And at what level does it become not important? And if you look at, you know, you talk to engineers and people who have houses on the ground, those small little incredible tight, strong vortices matter. I mean, all you've got to look back is Andrew and some of these landfalling systems that will, you know, hit one house. It's almost like tornado kind of damage. But now we're getting close to being able to observe and dare I say model that. So I think that the verification and the tools that we have now allow us to do more, and we just gotta sit down and figure out how to do it.
And let's not forget Hugo, Frank.
Pete, speak up. Can't hear Pete. And then we'll go to George.
Yeah, no, I just said, I was suggesting that you don't forget Hugo with the mesovortex that we flew through. And that's not just an isolated case.
Don't forget that. Go ahead, George.
I wholeheartedly agree with what you are saying, Frank. Different measures of intensity and structure, and even intensity structure combined. So my suggestion there is just start doing it, and then start looking at some metrics, or start doing some analysis from data and models, and see how they do. It'll catch on, I think.
Well, I'm looking at Chris because Chris ran the reanalysis project, and you've been looking at modern methods of estimating the things that we need to measure for the HRDAT. And now, in light of the things that you're seeing now, do we have to revisit that? And, you know, we're talking about a reanalysis, you know, to help us better understand. Question is it making you rethink some of these things?
Well, yeah, you can always go back and apply today's understanding on older data, but we can't go back and get SAR data from 1973. That's the problem. And so technology infuses everything we do, and it influences the database. And so when one wants to compare storms now versus 100 years ago, or even 10 years ago, it's tough because we observe them so much more finely and so much more accurately today. So it's, but, you know, we don't need to go down that climate rat hole today.
One area that actually we wasn't really discussed so much in this session, but is important, is the wind measurements over land. That's a whole area that the local forecast offices have to deal with, and they tend to do it through the 3-second gust. What the sustained winds really mean when you're inland is you hardly ever observe hurricane winds inland. It's sustained winds, but gusts you get all the time. So I think one area where I think there could be a lot of improvement is dealing with how do you handle it over the land. And thinking about Georgia's simulation, that was probably over water, I'm guessing. That just imagine if you put in variable surface roughness, what it would look like. I think that's a problem that, you know, we need to deal with to improve the inland warnings, but we haven't really scratched the surface there.
Hey, Mark, did you look at the anemometer data from Otis that was taken in a marina there, showing gust factors, so-called gust factors of about factor of 2 rather than 1.2? It's a good example of that problem, I think.
Which one is that? George showed that. He showed 2.7 gusts, but.
Yeah, we're doing a lot of research for an HFIP project that Mark's leading on gust factors, try and estimate them through HAFS. And just the observations from ASOS are showing a very large variability in magnitude as a function of wind speed. And I'm just looking at a plot right now in front of me, just at the 70 to 80 knot sustained winds, we have gusts up to, 1.7. And the minimum was about 1.4, which is a lot higher, I think, than currently is, sort of used operationally. So I think that, high gust factors are really not that rare. And, the values cited are medians or means. They're really not the, upper percentiles, which are probably the more important ones.
I ask you a question on that real quick. When you said in comparison to ASOS, are you putting them through the same type of algorithms? So you're comparing apples to apples? Because ASOS has multiple algorithms on the wind for whether it be sustained or gust, or whether it be the 2-second, 5-second, et cetera winds.
ASOS 2-minute average versus 3-second gust.
Okay.
Looked at every
So
minute.
there's a lot of smoothing difference there then. If you're talking 2-minute.
Yeah, but the gust factor
the ASOS transducers go every 2 seconds. So 2 minutes is a lot different than 5 seconds in that case.
Yeah, I guess I don't follow the gust factor is a 3-second gust divided by the.
But you said you're taking a 2-minute wind.
Correct.
The measurement sampling rate on ASOS is about 2 seconds.
I think it's a second.
Okay, that's even worse.
But it's the average of the 1 second. It would be times 2, 120 1-second values.
Oh, okay. I
running
thought
main-
you meant you were taking a 2-minute wind, not 100. Okay. All right.
It's a 2-minute average wind computed from the 1-second data.
Okay.
Yeah, the weather flow data is even higher, but that's what the ASOS data show, and that's looking at it every minute. So they have they compute that every minute. So
I had a question for Stephanie, actually. People are in my way. You had an analysis where you showed different observations, and there were violin plots. And I noticed that almost every one was less than the NHC estimates or best track. I have to learn a little bit about the differences. Why was it seemed to be this mean underestimate for like almost every platform except for SAR, if I recall correctly?
So those were the medians that were plotted, but yeah, they did tend to be a little bit under. For the aircraft data in particular, that's including all the flight legs, so it's not capturing the strongest part of the storm on all of those. I have to do some more QC to pick out the strongest leg versus the one that goes against that. ASCAT we know doesn't capture the resolution, but the others were kind of centered around 0. The satellite estimates and Dvorak. Yeah.
I have a question for the general modeling community, I guess. I know the Navy has a capability of looking at the impact of individual data, individual observations. Do we have that capability at within EMC to do that sort of thing without having to do a full-on OSI experiment? Who wants to answer that?
So the IWS community actually hired one person who can pay pretty much attention to the adjoint method. So that method is a sort of coming from the encoder data simulation package. So he's working on this one. So hopefully, he said the package is pretty much done by this week, and the next week he can give us some some results too. So next week. Yeah, so that's the ocean side.
Daryl, can you give us an
that's the
insight
ocean side.
into what's going on at EMC?
That's the ocean side. So think about it. Atmospheric side.
So first I have to interpret the question, and I think you're referencing something like an FSOI, which is a projecting forecast errors back onto the observation space. So looking at the impact of a simulation of an observation and reducing forecast error. So that's one way to measure impact. That has to come with lots of caveats. We do not have an adjoint yet working for FE3, so we don't have it for HAFS, although through collaboration with GMAO, we do have access to a version of the adjoint for FE3 that we can plug into things like JEDI or even GSI to do these kinds of calculations. Separately, we had a long-standing project. We do have an EFSOI capability. So it's a pure ensemble-based estimate that we can run for the global. We've never tried to apply it to the regional systems, but it's GSI-based. It's more workflow than infrastructure. It can be done. It comes with some caveats. In the DA community, one of the things we noticed is the ensemble-based estimates tend to be outliers when we do direct comparisons to adjoint-based estimates. So there are ways to do this kind of thing, but like anything, you have to sort of take into account the caveats that come with being able to interpret what it actually means. Separately with GMAO, there's also another version that comes directly out of the hybrid assimilation system that we could explore. It's in GSI. It's available. I don't think anyone's tried to exercise it for HAFS, but it's something we could look at.
Thank you. That's encouraging.
You've got about a minute.
I guess I'll ask a question to the modelers. You guys do VI. You take what the Hurricane Center thinks is the wind and the center position. Are you feeling comfortable using that now after all this stuff you heard? I hope not.
Well, it's interesting, you know, comment on that. Oh, Gus.
No, it's sort of related. I was going to bring this comment up, but you know, one thing that I learned doing some work with Zach and Joan is, you know, the high frequency output that's coming out of the model is very different than the instantaneous output we take every 3 hours. And so we have to be very mindful of that when we're verifying maximum wind coming out of the model. And what we found in the work that Zach led is that by taking the high frequency output, this was an HWRF, putting a running mean on that, about a 6-hour running mean, it actually verified better with the best track than just taking the instantaneous output every 3 hours. So again, I think we also have to be mindful, you know, what are we comparing against and what are we actually getting from the model? So I think that's kind of a low hanging fruit we should start thinking about right away in terms of how we look at the model output.
I will just quickly add what Gus said. Basically, this is also my question for the observation community. We have a lot of observation available for the forecasters. A lot of question I had was how many of these observations are available in real time? How many of those data can be assimilated in their model? That's one question. Another question is to comment for the VI one. I think it would be very, very nice. We have all these data available for the model for not only verification, but also for the analysis. I think we talk about the analysis products. I think that, yes, I think that will be very important aspect for the model development as well. I think another thing quickly, actually there are a lot of cycles in the open ocean. We actually do not have too many data over there. So think about that. I think that's one of the major reasons we are still using VI.
Thank you, Ben.
The UAS data is definitely getting to the GTS. Whether it gets out of the GTS is another question, but that should be real time. And one last comment about the track and the small scale stuff. Actually from AOML showed that this is going back a generation before, not even the current generation of UAS. We're always thinking structure and intensity change. That's where we're looking in the boundary layer. One of the most surprising facts we got was it impacted the track. And it was because it re-centered where the storm was very accurately because we were flying in a little plane in there, and that data gave a much better track, and it was significant. So that could make a difference at landfall, particularly.
All right, thank you, everybody. We're going to take about 13-minute break. I'll be back at 3:30, and we'll start our session on DA. It will be chaired by Jason Sipple and